Every single time you visit a website starting with HTTPS, your device and that website agree on a secret code. In public, in full view of anyone who might be listening. And somehow, no eavesdropper can crack it. Here's exactly how that works. Imagine you want to send a secret message to a website, like your password, but the connection between you passes through equipment you don't control or trust. Anyone quietly monitoring that connection can see every single bit of data you send, unless what you're sending is genuinely unreadable to anyone except the intended recipient. In reality, this connection might pass through your Wi-Fi router, your internet service provider's equipment, or several other networks entirely outside your control, any one of which could theoretically be watching. For centuries, encryption meant simple substitution, like the Keyser cipher, where every letter is shifted a fixed number of places in the alphabet. The huge weakness here is that the same letter always becomes the same substitute letter. Patterns from the original text leak straight through into the encrypted version. This lets attackers use something called frequency analysis. Certain letters, like E in English, appear far more often than others in any normal piece of writing. And that statistical fingerprint survives simple substitution completely intact. Given enough encrypted text to work with, frequency analysis can crack ciphers like this in a matter of minutes, without ever needing to know the original secret key at all. Even a genuinely strong cipher has a deeper problem. Both sides need to agree on a shared secret key beforehand to actually use it. But how do you securely share that key in the first place? Over the exact same untrusted connection you're trying to protect. This is called the key distribution problem. And for decades, it seemed unsolvable. In the 1970s, researchers found an elegant solution. Imagine an open padlock that anyone in the world can snap shut, but that only one specific key can ever open again. The website can publish that open padlock completely publicly, for anyone to use, but only the website itself holds the private key needed to unlock it again. This completely solves the key distribution problem from before. The public lock itself can travel over a completely untrusted connection with zero risk, since it's genuinely useless to anyone without the matching private key. Here's the full picture. The website sends you its public lock, openly, over the internet. You use that public lock to seal your password inside a message. Once locked this way, not even you can unlock it again. Even someone watching this entire exchange only ever sees the locked message travel across the connection, without the website's private key. That locked message is functionally useless to them. The real magic behind this is a mathematical one-way street. Multiplying two prime numbers together is easy, and takes a computer almost no time at all. But going backward, taking a massive number and figuring out exactly which two prime numbers were originally multiplied together to create it, is brutally, deliberately difficult, even for powerful computers. Real-world encryption uses numbers that are hundreds of digits long. Factoring a number that size would take ordinary computers dramatically longer than the current age of the universe to brute force. This fundamental asymmetry, trivially easy to multiply forward, but nearly impossible to reverse, is the entire mathematical foundation this whole system is built on top of. That little padlock icon you see next to a website address represents this entire exchange. happening automatically, in well under a second, before the page even finishes loading. Every login, every online payment, and every private message sent through a secure messaging app relies on this exact mathematical process, running silently in the background. In practice, this public key system is actually only used briefly, at the very start of the connection, to safely exchange a much faster, temporary key that handles the rest of your entire browsing session. A problem that once seemed genuinely impossible to solve, sharing a secret over a connection you don't trust at all, was solved entirely with pure mathematics, and it now runs quietly behind almost everything you do online. So the next time you notice that small padlock icon next to a website address, remember it represents a genuine mathematical breakthrough, quietly working in real time, every single time. Thanks for watching. Subscribe for more science visualized.